Hi again. Again, I'd like to apologize for the background noise, but let's continue. Today, or now, I want to talk about indices, and these indices are going to start from cardiac output being equal to heart rate times stroke volume. We just want to appreciate some things that can affect heart rate and stroke volume, and therefore increase or decrease um, the output uh, of the heart or of the ventricle. Now, remember that usually when this is being talked about, though the atria does affect the ventricle, you're really talking about what the ventricle is able to put out, and of course, what it's able to put out will be highly dependent on what it's receiving. So, with that in mind, I'd like to start with heart rate. The first thing we see affecting heart rate is the sympathetic or the autonomic nervous system. So we have the sympathetic and the parasympathetic. So the parasympathetic happens in such a way that um, when the autonomic system is tilted to the parasympathetic, we have it reducing. Okay, so it reduces heart rate. But the sympathetic has been noted to increase heart rate. Now, we went through these mechanisms, I think, a while ago, and so please go back to how this happens. The other thing that the sympathetic does is it causes vasoconstriction. Now, vasoconstriction is simply the reduction of the vascular uh, diameter. So when it moves from this to that, you're going to have an increase in pressure. So when there's an increase in pressure, if you are talking about the venous side, let me just draw. If this side is the right and this side is the left, you have the arterial going to the tissue, and from the tissue you have it going back to the heart on the venous side. So if this side is constricted, you have increased pressure to the heart. And if there's increased pressure to the heart, we call this an increase in venous return. Okay, all right. So it causes vasoconstriction, which leads to an increase in venous return. Okay, let's go to the stroke volume. The stroke volume, as I said, is literally how much blood comes out due to an impulse from the SA node. So what does affect this amount or this volume of blood per impulse? The first thing that I will talk about is preload. Now, preload is the amount of load or the amount of pressure that is on the ventricle before it starts contracting. Now, if you go back to your mathophysiology, you will notice that when the sarcomeric unit is not in a fully relaxed state, it actually contracts more. All right? So go back to that theory, because it's the theory that we are now building up on. So if you find that the ventricle is relaxed, highly relaxed, it won't contract as much when the depolarizing wave comes in. But if it has a little load on it, okay, if it has a little load pre or before it starts contracting, if it has a preload, you will find that the contraction will actually be more. So if the contraction is more, it means that whatever it's going to put out will be more. So stroke volume is going to increase. So what is this preload that we're talking about? If you remember our cycle, at this point we're talking about the fact that there is some blood, there's a volume of blood before contraction starts. So this is the end diastolic volume that we are talking about. So we note that preload is dependent on the end diastolic volume. And the end diastolic volume, when it increases, it will increase preload. Okay? Another factor that I would want you to take away from increased preload is that there will be an increase in this EDV if what is returning to the heart is more. Okay? So if you have an increase in venous return, you will have an increase in EDV. And if you have an increase in EDV, you have an increase in preload. If you have an increase in preload, therefore your stroke volume will be higher. Awesome. The other thing that I would want to talk about here is something known as feeling time. Now we're going to come to this really soon. I just want you to keep this in mind. Feeling time. Alright, having said that, the next one I want to talk about is contractility. Now in contractility, you're simply talking about how fast the heart is beating. So if it's beating faster, you will find that it will bring out more blood. Okay, so contractility is how fast the ventricle is contracting, and so you find that if it's higher, the stroke volume, of course, will be higher. It is reduced in certain pathologies, and when there is certain pathologies, you'll find that this is reduced when the muscle itself has been affected. You'll find that it does not have an ability to contract that much, and so you'll find that cardiac output is ultimately affected. The last one I'd like to talk about in this video is what is known as afterload. Now, afterload is this pressure that the ventricle has to work against in order for blood to move out. Now, if you remember, we did say that the ventricle will have to overcome 80 millimeters of mercury, which is the resting, if I can draw that again, it is the resting pressure for the aorta. Okay, so it has to work against this pressure. Okay, so for this to open, for the aortic valve to open, it has to overcome a pressure of 80 millimeters of mercury. So this is what is known as the afterload. Now, if by any chance, now it's not chance of course, but if by some mechanism we find that this pressure of 80 increases to, let's say, 110, the ventricle will have to work harder to overcome this pressure of 110 so that blood can go out. Now, what is happening here is, I beg your pardon, let me just delete that, is as you go away from the ventricle, okay, so if this is the ventricle, as you go away from the ventricle into the aorta, you will find that there are arteries that then go into arterioles. And these arterioles have, they're highly masculine, or they have smooth muscle around them. So if this muscle contracts, you find that there is less excess here, so there will be less blood going to the venous side. So if there's less blood going to the venous side, it means more blood is kept in the arterial side. Okay? If there is more blood in the arterial side, the pressure will increase. So if arterial pressure increases, it means that in the aorta, pressure will also increase. It won't be at 80 millimeters of mercury anymore. So then what the ventricle has to work against will be higher. Okay, so this is one way in which afterload can be increased. So maybe just to summarize what I'm saying, I will state that it is affected by aortic pressure. Alright, so if aortic pressure increases, you find that afterload will increase, and if afterload increases, okay, it will decrease stroke volume. Okay, so this one works inversely, whilst preload works proportionally. So why does aortic pressure increase? We're talking about it being affected by total peripheral resistance. Okay, and why does total peripheral resistance come in? Because of this constriction that we talked about here. Alright, so having said that, now I just want to bring something into perspective. So I have a question. We say carbon dioxide, sorry, does look like, okay, we say cardiac output is equal to heart rate times stroke volume. Okay, if you have a heart rate of 50 and a stroke volume of 50, what is your cardiac output? So in this case, you're talking about an output of about 2,500 mils per minute. What if your heart rate increased to 60, but you noted that the cardiac output was the same? You would think that in this case, you have one of 3,000. And that's how it's supposed to kind of work. But there is a relationship between the heart rate and the stroke volume, which we are not really talking about, and that is where feeling time comes in. Now, initially, this is what you would see. You would see an increase in cardiac output because there's increased heart rate. But what will happen in this case is, as heart rate increases, what you are doing is you are reducing. Let me go back to our heart. All right, so we have an impulse coming in, all right, at 0.1, and then it is delayed here. Why is it delayed? So that enough blood can go into the ventricular side, and once there is enough blood here, then the cardiac output is going to increase. Okay, because you're going to have more blood in a minute coming out of the heart. But if you're going to place another impulse really close, it means that you are reducing this time. So if you are reducing the time that the ventricle has to fill up, it means that your EDV is going to reduce. If your EDV is going to reduce, it means that the stroke volume will reduce, and therefore your cardiac output will reduce. I'll say that again. Because you have an increase in heart rate, at first you will have increased cardiac output. But as time goes on and you have the heart rate keeping on racing, or the heart rate keeping on being high, what you're going to reduce is you're now going to, I beg your pardon, you're now going to reduce the feeling time. okay, of the ventricle. If you're reducing the filling time of the ventricle, it means the ventricle is not receiving enough blood. So it means the EDV, okay, the EDV is going to reduce. And if the EDV is going to reduce, this means number one, preload has reduced, and number two, amount of blood to take out of the ventricle has also reduced. So if you are reducing these two, it means that the stroke volume will reduce, and ultimately you are reducing cardiac output. Okay, let's take an example here of running. When you are running, you are increasing your sympathetic, or your sympathetics kick in. So if your sympathetics kick in, the first thing that they will do, let's look at sympathetics. The first thing that you will note is, number one, they will increase or they will change vascular tone. And how will they change vascular tone? All right, they will increase constriction, and so you have more heart, more venous return. More venous return is good. Why is it good? Because you have more blood to the ventricle, and if there's more blood to the ventricle, that means you have increase in cardiac output. So this is a plus, okay? But that's just one of its effects. Secondly, you will find that it will reduce the flow of blood to places like the GIT and shunt it to muscle. So there's shunting of blood to muscle. This is good as well because you want to have as much oxygen in the muscle which you are using to do the exercise. So this is also good. Let's look at another consequence. Because you are increasing the heart rate, again, you're going to have a reduction in filling time. And a reduced filling time, this is a no-no. Why? Because as we have just explained, this is going to reduce cardiac output, and we don't want that to happen. Now let's make this worse. Let's say you go running and you are dehydrated. So what's going to happen? If you are dehydrated, there will be constriction going on, but even though there will be more venous return, you don't have enough, okay? You are dehydrated. You don't have enough to return. So if you don't have enough to return, it means your EDV is going to go lower, preload will also go lower, and finally cardiac output will also go low, and we don't want this to happen. The shunting of blood, it won't be also enough because you are dehydrated. Again, the heart rate, it will kick in. You will have reduced cardiac output on number 3, as well as number 1. The muscle won't be receiving enough oxygen, and what you have here is what is called fainting or syncope. What is one way that we can apply this? Okay, so having talked about that, in our next video we'll be talking about